October 1st, 2025, just past midnight. The US government grinds to a halt. NASA's site goes dark. Social feeds stop updating, and right then, at that very instant, a mysterious interstellar object, called 3I Atlas, drifts into view near Mars, 30 million kilometers out, exactly where our orbiters already have their cameras fixed on the heavens. Coincidence? Maybe. But here's what kept me awake as it happened. The timing feels too perfect, almost like a script. Was this just government chaos, or the most convenient blackout in recent space history? Stick with me through this late-night deep dive, because by the end you'll see what really unfolded in those silent October days, what the data reveals, and why this event matters far more than most realize. Part 1. The shutdown and the arrival. The unsettling coincidence. First, let's unpack exactly what we're dealing with here. On October 1st, 2025, the United States government officially entered a shutdown. No fireworks, no press conference countdowns, just a subtle bureaucratic click. The funding dried up, and the lights went off. Federal websites froze, agencies went dark, and NASA, the same agency that once walked humans on the moon and drove robots across Martian deserts, posted a single stark banner on its homepage. NASA is currently closed due to a lapse in government funding. For most people scrolling headlines that Tuesday, this was another round of budget gridlock in Washington. Nothing unusual. A routine performance of political brinksmanship. But here's the detail that should stop you mid-scroll. At almost the precise moment NASA's public voice fell silent, the third confirmed interstellar visitor in recorded history reached its closest approach to Mars. The timing was razor-sharp. This object, designated 3I Atlas, also catalogued as CM25N1, wasn't from our solar neighborhood. It wasn't a leftover rock circling our star since the system formed. This was something else entirely, a traveler from the void between suns, hurtling in on what astronomers classify as a hyperbolic orbit. In plain language, that means it's not tied to the sun's gravity. It's a one-time guest, just passing through, never to return. We've only verified 2 others before it. The first was Oumuamua in 2017, a cigar-shaped riddle that launched endless debates about whether we'd glimpsed alien technology for the first time. The second was Borisov in 2019, which looked much more like a normal comet, and soothed some nerves. But 3I Atlas, or 3 Atlas as it's often nicknamed, is number 3. It was discovered on July 1st, 2025, by the Atlas survey system, appropriately named, since that's literally where its designation came from. Meanwhile, across the Atlantic, the European Space Agency, ESA, had lined up a very different plan. They'd scheduled a dedicated observing campaign for October 1st through October 7th, using their 2 primary Mars-orbiting spacecraft, Mars Express and the ExoMars Trace Gas Orbiter. The geometry was ideal. On October 3rd, the comet would swing within roughly 30 million kilometers of Mars. That might sound enormous on earthly scales, but in astronomical terms it's practically shoulder to shoulder, a cosmic handshake. Mars, not Earth, would have the premium vantage point to watch this interstellar stranger pass by. ESA's orbiters, equipped with high-resolution cameras and advanced spectrometers, had front-row seats to a spectacle no human instrument had ever captured. A close-range look at an interstellar object from a planetary base other than Earth. But here's where the story twists into something far more unnerving, the kind of detail that prickles at the back of your neck. During a government shutdown, NASA suspends the majority of its outward-facing operations. Websites freeze. NASA TV goes offline. Press releases halt. Social media accounts stop posting. The agency's communication machinery, which normally churns out breathtaking images and constant updates, simply shuts down. Only accepted operations, the activities legally required to protect life and property, continue. The International Space Station keeps running. Essential satellites stay online, but the public can't see what's happening behind the curtain. It isn't malicious. It's written into appropriations, but the effect is the same. The lights flick off at the very moment something extraordinary unfolds in our cosmic backyard. So why did audiences hear so little about 3 Atlas during this crucial window? Part of the answer is straightforward. NASA's shutdown meant fewer personnel monitoring data streams, fewer staff writing press releases, fewer people authorized to tell the public what was happening. But another factor made things even worse. From Earth, 3 Atlas was extremely difficult to see during this period. Its low elongation, its apparent closeness to the Sun from our vantage point, made ground-based observations nearly impossible. Imagine trying to photograph something faint when it's next to a blinding spotlight. Ground telescopes struggle. The Martian orbiters were our only real eyes during those critical days. And those eyes belonged to agencies operating under radically different rules. ESA proceeded as usual, while NASA fell silent. It's worth noting that Hubble had already snapped images of the comet back in July, which gave astronomers some constraints on the size of its nucleus. But those measurements were incomplete. Without a precise nuclear size, the mass remained an open question. And without the mass, composition became a guessing game. Was this an ordinary comet of ice and dust? Or something denser, stranger, more exotic? The uncertainty left wide gaps for speculation. And speculation, as you're about to see, is exactly what filled the void during that quiet October week. Let's lay out the timeline so you can see the synchronicity for yourself. July 1st, 2025. Discovery. The comet is spotted. Its trajectory is calculated. Astronomers realize they're dealing with something special. October 1st, 7th. The Mars window, the optimal period for close-range observation from Martian orbit. October 29th, 30th. Perihelion, the comet's closest pass by the Sun. Late November-December, the object reappears to Earth-based observers after solar conjunction. During that October window, when this interstellar visitor was most accessible to our robotic explorers, NASA's public voice went dark due to a bureaucratic switch. Online, rumors started instantly. Whispers of missing images, telemetry gaps, frames uploaded and then removed, redacted data files, unscheduled spacecraft maneuvers. Most of it was noise, the usual rumor mill that thrives in information vacuums. But a few claims were harder to dismiss. Were there real gaps in the data, or just gaps in communication? That's the question we're going to untangle. We're going to follow the paper trail. We're going to parse spacecraft logs and orbital mechanics. We'll test whether the silence was a coincidence or something else entirely. Because here's the uncomfortable truth. If you wanted to observe something in deep space without the public noticing, a government shutdown would be the perfect cover. Not because of conspiracy, but because policy already provides the mechanism for silence. Those mechanisms were absolutely in effect. That's not speculation, it's law. The question isn't whether those mechanisms existed. They did. The question is what happened while they were active, and whether the official narrative matches reality. Was this just an unnerving coincidence, or a perfectly timed curtain drop over something we weren't meant to see clearly? Let's start by identifying who was actually watching from Mars, and why the silence around them felt so chilling during the days that mattered most. Part 2. The planetary observers and their silence. If you want to understand why this blackout felt so dissonant, you need to know exactly who was in position to see 3 Atlas up close, which spacecraft were circling the red planet, and what they were supposedly doing at the time. On the American side of the Martian sky, NASA commanded a formidable lineup of spacecraft, chief among them the Mars Reconnaissance Orbiter, equipped with its world-class high-resolution imaging science experiment, HIRISE for short, essentially the most powerful telescope ever sent to orbit another planet. Alongside it was MAVEN, the Mars Atmosphere and Volatile Evolution mission, which focuses on the thin upper atmosphere of Mars but also carries instruments capable of reading the solar wind and plasma activity around the planet. And down on the ground, crawling the rusty surface, Perseverance and Curiosity rovers continued their steady work. These rovers were not built for comet science, but in theory, with proper instructions they could turn their cameras skyward to capture wide-angle frames or photometric snapshots of a passing object. On the European side, ESA was clear and transparent about their plans. They openly announced an observing campaign running from October 1st through 7th, perfectly timed to coincide with 3 Atlas's closest pass at roughly 30 million kilometers on October 3rd. Their stated objectives were concrete: extract hints about the comet's shape from its coma, measure its activity levels, and gather spectra to infer its composition. This wasn't some clandestine experiment. ESA's mission scientists gave interviews to outlets like Space. They explained the unique geometry, the daunting challenges of observing such a faint object at that distance, and their genuine excitement at the opportunity to scrutinize an interstellar visitor up close. This was the sort of normal, open mission engagement the public expects when a science agency does something historic. NASA's position during the shutdown, however, was different, but not, at least officially, sinister. Its continuity of operations plan, which anyone can read in public records, spells it out plainly. Spacecraft operations continue during a lapse in appropriations if necessary to protect property and life. That's the legal phrase. In practical terms, it means the orbiters keep flying and their health is monitored. Thruster burns to dodge debris or adjust trajectories still happen. Essential communications with spacecraft still happen. But public communications pause, websites stop updating. NASA TV goes dark except for minimal ISS coverage. The press office sends everyone home. So here's the operational picture. NASA's Mars assets were capable of operating during the shutdown, and almost certainly did operate at some level. What didn't happen was the public reporting about what, if anything, they were actually doing. This brings us to the crucial difference between confirmed plans and speculation. ESA's observing campaign is on the record. They said they were doing it. Their goals and statements can still be found in archived press releases and interviews. NASA, by contrast, made no official announcements about MRO or HiRISE targeting the comet during the Mars window. That doesn't prove they didn't try. It only shows we lack confirmation. In the run-up to October, several planetary scientists, including Avi Loeb, the Harvard astronomer who has been one of the most vocal proponents of the idea that Oumuamua might have been artificial, publicly expressed hope that HiRISE would be tasked to observe 3 atlases. Loeb has a well-documented history of pushing for aggressive campaigns to monitor interstellar objects, but there's a difference between public expectation and institutional confirmation, and this is where capabilities matter. HiRISE, the high-resolution imaging science experiment, is a phenomenal camera by spacecraft standards. Orbiting Mars, it can pick out features as small as 30 centimeters across on the surface below, but 3 Atlas wasn't sitting on the Martian surface. It was 30 million kilometers away. At that kind of range, HiRISE's resolution collapses to something like 30 kilometers per pixel, perhaps slightly better under ideal conditions. You're not going to resolve a nucleus. You're not going to photograph surface features. What you could do is photometry, measuring the brightness of the object, and how that brightness changes over time. With careful analysis, you might detect asymmetries in the coma, the gas and dust envelope surrounding the nucleus. You could extract shape information from its light curve. That's scientifically useful, but it's not the kind of crisp, close-up imagery most people imagine when they hear HiRISE pointed at a comet. From Earth during that period, 3 Atlas was extraordinarily difficult to observe. Its low elongation, its apparent closeness to the Sun from our perspective, made it a nightmare for ground-based observatories. Pointing sensitive instruments near the Sun risks damage and blinding glare. Some observatories managed limited observations during twilight, from high-altitude sites, but these were far from ideal. All of this made Mars-based assets uniquely valuable. They had the geometry advantage, looking at the comet from an angle that avoided the Sun's glare. If humanity was going to collect good data during early October, Mars was the place to be. Now let's address the silence directly. During a US government shutdown, NASA's public-facing outputs grind to a halt, website updates slow to nothing, NASA TV ceases its normal programming, social media accounts post nothing, press offices don't issue releases. This isn't improvisation, it's a direct consequence of policy. The Anti-Deficiency Act, the federal law that governs agency behavior during funding lapses, prohibits spending money the government doesn't have. That includes paying web developers to update sites, paying public affairs officers to write releases, and even in some cases covering server costs. The result? Informational silence. But that's not the same as operational silence. The spacecraft keep flying. Data continues to stream down, at least the essential health and safety telemetry. What doesn't happen is the curation, processing, and public release of scientific data. As of October 1st, there were no NASA press releases about Mars Reconnaissance Orbiter or the rovers capturing images of 3 Atlas. Is that suspicious? Not necessarily. It's expected during a shutdown. Even under normal circumstances, science results take time to process, analyze and release. During a shutdown, that pipeline is completely frozen. The data could be sitting on a server right now, waiting for scientists to return to their offices, and for funding to resume so they can get paid to analyze it. Or the observations might not have been made at all, or they were made and yielded nothing of immediate interest. Without official confirmation, the public is left to speculate. Here's what we can say with confidence. ESA openly stated they were observing the comet during the Mars window. NASA's assets were capable of observing it, and safety-level operations continued during the shutdown. But NASA's public communications were paused by law. That created a stark divergence in narratives. From Europe we got statements of intent and excitement. From the US we got silence. Not because NASA scientists didn't care, but because the machinery of public communication was switched off. That silence, combined with the extraordinary nature of the event, an interstellar visitor passing Mars during a rare US government shutdown, produced perfect conditions for speculation to bloom. And bloom it did. When official channels go dark, unofficial ones light up. The question now is whether that noise contains any genuine signal, or if it's just the echo of collective anxiety in an information vacuum. Did the silence hide actual gaps in publicly accessible data, or was it simply the predictable frustration of losing access during a funding lapse? That's what we're about to examine. Part 3. Data gaps, redactions, and the dead zone. Welcome to what I'm calling the dead zone. October 1st through 7th, 7 days when one of the most intriguing interstellar objects in years was at its most accessible to our Martian orbiters, and when NASA's public communications apparatus was effectively frozen, not offline, not censored, but administratively paused by law. This is the period where fact and speculation blur, where absence of information itself becomes a kind of information, and where the human instinct to connect dots can create patterns that may or may not be real. Before we wade in, we need to establish what counts as a real gap versus what's simply normal shutdown behavior. During a federal government shutdown, NASA is mandated to scale back its online presence to a bare minimum. Instead of its usual active pages, the main nasa.gov site typically displays only a stark closure notice. Mission-specific pages that normally push out fresh updates stop posting new information. Image repositories that would otherwise fill up with the latest pictures from Mars rovers and orbiters go still. News feeds stop rolling. Social media accounts fall silent. All of this isn't a mystery. It's explicitly laid out in NASA's publicly available Continuity of Appropriations plan. That plan spells out in clear language that public access to many NASA-run online services will be interrupted during a funding lapse. There's no hidden agenda here, so if you happen to be monitoring NASA's websites during the first week of October and saw a freeze in activity, it wasn't evidence of censorship. It was proof that NASA was following its policy to the letter. But here's where the story gets more intriguing. Not every space agency mirrors this behavior. While NASA was dark, the European Space Agency continued posting as usual. Space.com, an independent media outlet covering space exploration, kept pushing out stories. Amateur astronomers and their networks continued publishing their own observations. Third-party satellite trackers kept releasing updated orbital data. In other words, the information blackout wasn't global. It was uniquely a US government phenomenon, centered squarely on NASA. That mismatch in data flow created a lopsided information landscape. European and independent sources were actively discussing 3IATLS, while official American channels were silent. Even if entirely innocent, that asymmetry can feel like concealment. Bureaucracy can look like secrecy. So how do you tell the difference between a normal shutdown gap and something truly anomalous? Real red flags would include raw images scheduled for release before the shutdown, but never posted, telemetry arriving incomplete or with nonsensical timestamps, observing slots listed in science schedules producing no corresponding data products. or spacecraft maneuvers appearing in trajectory files with no matching entry in operational logs. Those are the kinds of signals that something beyond normal policy might be happening. But in early October, when the shutdown had just taken effect and NASA's data pipelines were essentially frozen, everything looked like a gap, simply because nothing new was being made public. It's important to make one thing absolutely clear before going further. There's no confirmed evidence that 3IATR's data collected during the Mars observing window was formally classified. Classification is a precise legal mechanism. It requires explicit authority, written orders, and justification under national security criteria. Nothing in the public record indicates such orders exist for this comet's data. Speculation about classified space data is exactly that, speculation. And once that idea enters a conversation, it tends to snowball. People assume secrecy automatically means something extraordinary, but the lack of evidence for classification is not itself proof of transparency. It simply means we're not dealing with official secrets. We're dealing with an informal silence caused by policy. Nevertheless, the speculation came quickly and loudly. Within days of the shutdown, YouTube channels dedicated to UFOs and anomalous phenomena began focusing on 3. Reddit threads surged with claims. Some posts said raw Mars reconnaissance orbiter images were uploaded briefly and then removed from archive servers. Others argued that FITS files, the standard format for astronomical data, showed pixel-level signs of redaction. Still others claimed spacecraft had made unannounced burns during the observing window, maneuvers visible in telemetry, but unexplained in public-facing logs. These are all presented here as unverified claims, not established facts, but they matter to the narrative because they shaped public perception during NASA's dead zone. As always, unconfirmed internet stories are hypotheses waiting for data, not evidence in themselves. So how do you actually test claims like these? How do you separate genuine anomalies from misunderstandings or fabrications? Here's a straightforward checklist you can apply once data becomes available. First, examine the timestamps. Do observation dates line up with pre-shutdown schedules that ESA and other agencies publicize? If images or spectra expected on October 3rd, the date of closest approach later appear with matching October 3rd timestamps, that's consistent. If they show up with mismatched or missing date metadata, that's suspicious. Second, check the instrument configuration. Every observation includes metadata about how the instrument was set up, filters used, exposure times chosen, operating modes. If multiple independent observers with different setups report similar findings, that's a strong cross-validation. If one lone observer reports something drastically different, that's a red flag. Third, cross-calibrate with ESA's public data. Mars Express and ExoMars observations should align with any NASA results. Brightness, position, and activity level should agree across independent sources. If they don't, someone's data is wrong or incomplete. NASA's own continuity plan even allows for the complete shutdown of its website or its reduction to a static placeholder page. That means you should expect no real-time updates or normal cadence of image releases during a lapse. Only batch releases after funding resumes. That's standard. What would be abnormal is if months after the shutdown ends, no Mars window data from NASA assets appears despite clear opportunity and capability. That would raise two possibilities. Either the observations never happened, an enormous missed scientific chance, or they did happen but are being withheld, which demands explanation. Skeptical patience is warranted. From Earth's viewpoint, the comet passes into solar conjunction in late October and through November, making it hard or impossible for ground-based telescopes to see. It re-emerges by late November into December. That post-conjunction window offers the perfect chance to verify any extraordinary claims about its behavior in early October. If 3IATRS really brightened unexpectedly, showed unusual spectral features, or deviated from its predicted trajectory, those effects should still echo in the later data. The December and January observations will either confirm or refute the anomalies. Careful attention to detail, not speculation, will produce real answers. Here's what we know so far. The dead zone existed. That's indisputable. NASA's public communications went silent during the optimal Mars observing window. Because of the shutdown, speculation about missing or manipulated data appeared immediately. That's also but verified evidence of deliberate data suppression, as opposed to routine shutdown-driven delays, does not exist as of early October. Most gaps are policy-driven. Whether genuine anomalies lurk inside those policy-driven gaps is something only the reopened data pipelines can reveal. Until then, the dead zone remains exactly what it appears to be, a frustrating blank space in the timeline that could be perfectly innocent, or hiding something worth a closer look. And that ambiguity is precisely what drives people to ask the next logical question. Did the comet itself behave strangely, or is all of this just noise swirling around an otherwise normal celestial event? Let's examine the trajectory math and see if the orbit tells us anything the silence can. Part 4. Anomalous signals, Doppler shifts, and orbital perturbations. We need to discuss the comet's path, because here speculation meets mathematics, and mathematics doesn't care about government shutdowns or competing narratives. 3i Atlas is on a hyperbolic orbit. That's the first essential fact. Hyperbolic means it's not gravitationally bound to the Sun. It originated from interstellar space, is making a swing around our star, and then it's gone, never to return. According to the current orbital elements, perihelion, the point closest to the Sun, will occur around October 29-30, 2025, at about 1.36 astronomical units, slightly farther than Earth's orbit. On October 3rd, the comet passed within roughly 0.19 astronomical units of Mars, about 30 million kilometers. These figures come from orbit, fits based on observations from Discovery in July through September, calculated by the Minor Planet Center and confirmed by NASA's JPL Solar System Dynamics Group. Here's how orbital determination works in real life. Observers, professional and amateur alike, track the comet's position against the background stars. Each observation yields a right ascension and declination, cosmic latitude and longitude, plus an exact timestamp. With dozens or hundreds of such measurements as the object moves across the sky, astronomers fit a mathematical model predicting its path under the Sun's gravity. If the observations match the predictions, the orbit is solid. If there are residuals, differences between where the comet actually is and where the model expects it, you hunt for reasons. It could be measurement error, or it could be additional forces at work. Comets are notorious for non-gravitational effects. As ice on their nuclei heats up and sublimates, jets of gas erupt, imparting tiny thrusts, like miniature rockets. Depending on the comet's spin state and the location of active areas, this can nudge the orbit in subtle but measurable ways. Astronomers account for this with non-gravitational parameters, extra terms in the orbital equations. For most comets, these parameters are small but detectable, explaining positional residuals of a few arcseconds over months. For 3i Atlas, what we have as of early October is Hubble's Space Telescope imaging from July, which constrains nucleus size and confirms active dust production. The Hubble data sets an upper limit on the radius and reveals a developed coma, classic cometary behavior, not an inert. What we don't have yet are peer-reviewed reports of anomalous Doppler shifts, or unexpected delta-V events during the Mars window. Doppler shifts are changes in the frequency of light or radio signals, caused by motion toward or away from the observer. If a comet accelerates in a way not explained by solar gravity or normal outgassing, its spectral lines shift unexpectedly. Similarly, if you're tracking a comet's position with extreme precision, and it's not where your model predicts, that's a delta-V event. A velocity space-based telescopes and planetary radars can detect accelerations as small as fractions of a millimeter per second squared over days or weeks. It's incredibly sensitive. As of early October, public orbital solutions for 3i Atlas show no large unexplained acceleration. The Minor Planet Center's most recent fits are consistent with a comet experiencing typical non-gravitational forces. Its orbit remains hyperbolic, still on its way out of the solar system. There's no sign it's being diverted into a bound orbit or ejected faster than physics allows. Could subtle anomalies exist that haven't yet been published? Of course, orbital refinement is ongoing. As more observations are gathered, especially after its post-conjunction reappearance, the orbit will be updated. If something strange emerges that wasn't visible in the preliminary fits, it'll show up in the published elements. Both the Minor Planet Center and JPL update their data regularly, and it's public. Anyone can ESA's Mars Express and ExoMars campaigns aim to capture brightness variations and rotation hints. At 30 million kilometers, even their best cameras can't resolve the nucleus directly. What they can do is measure how the comet's brightness changes over time, a light curve revealing its spin state and shape. If the nucleus is elongated and tumbling, you'll see periodic variation. If the coma is asymmetric, say brighter on one side due to a jet, that creates a time-varying signal, these observations could reveal non-gravitational effects or structural oddities, but only after detailed analysis. As of shutdown week, ESA's results weren't published. That doesn't mean they found nothing, it just means the analysis isn't done yet. Science takes time. Now about the popular rumors floating in informal spaces. Some online discussions claim that classified military or national security tracking assets detected unusual Doppler signatures during the Mars window. It's true the U.S. Space Force and other security agencies track objects with powerful radar and optics, but there's zero public confirmation that they targeted 3IATLS, let alone found anything anomalous. Treating these stories as more than speculation would be premature without evidence. I bring them up only because they're part of the cultural narrative, not because they're verified facts. If outgassing jets did produce small accelerations, where would you expect to see them? In the orbital fits, of course, but also potentially in image. A bright jet on one side of the nucleus would create an asymmetry visible in the coma. Spectroscopy could reveal the jet's composition: water, carbon monoxide, methane, or something strange. Ground-based observers took spectra of 3IATLS in July and August, showing features consistent with typical cometary volatiles. If something radically different appeared in October, we'd expect preprints or papers by now. As of early October, no such papers exist. This all suggests the preliminary answer: 3IATLS is behaving like a comet. Here's my promise to you after the post-conjunction observations in late November and December, and once the Mars data becomes public, we'll revisit the orbital solutions. The Minor Planet Center will update its element. JPL will refresh its Horizons database. If the orbit shifted unexpectedly in October, those updates will show it. If the estimated mass changes significantly, we'll see that too. If new spectroscopy reveals something bizarre, it'll be public. The scientific process may be slow, but it's transparent. We'll have answers, and we'll measure them against today's claims. That's the test. Real anomalies will leave traces that survive peer review. If they're not real, the updated data will be gloriously boring. So what's the cautious, conservative view right now? Measurements through September support a cometary interpretation with normal activity. The hyperbolic orbit matches an interstellar origin, which is already extraordinary on its own. Claims of strange dynamics, unexpected accelerations, or military detections of odd signals remain unverified in the peer-reviewed public literature. That doesn't mean nothing unusual happened. It means we don't yet have evidence to say something definitely. And that leads naturally to the next speculative layer. If the dynamics aren't the curveball, maybe the composition is. Let's talk about the metal. Part 5. The metallic signature and its implication. Here's where 3IATLS begins to look truly intriguing, or deeply perplexing, depending on your appetite for uncertainty. We simply don't know how much this object weighs. Let me show you why that uncertainty poses such a major challenge. When Hubble observed the object back in July, astronomers tried to estimate the nucleus's true size based on how bright the surrounding coma appeared and how much dust it seemed to be producing. The resulting analysis suggested a nucleus somewhere between roughly 0.3 and 5.6 kilometers across, a range so wide it spans nearly a factor of 17 in diameter. And because mass scales with volume, that means the potential spread in mass is even greater. Why so much ambiguity? It's because we can't actually see the nucleus directly. It's simply too tiny and too far away for even Hubble's optics to resolve. What the telescope detected was the diffuse glow of the coma, the gas and dust streaming outward. From that, scientists have to reverse engineer an estimate of the solid body buried at its core. To do that, they must make assumptions about things like how reflective the surface is, its albedo, and how effectively it's shedding material. Change those assumptions even slightly, and your calculated size changes dramatically. The same Hubble dataset was used to estimate the comet's mass loss rate, how much matter it's ejecting into space each second. The models suggested anywhere between about 6 and 60 kilograms per second. Again, a tenfold uncertainty driven by unknowns like the size distribution of dust grains and gas production efficiency. Still, those numbers are consistent with a normally active comet. As a comet draws closer to the sun, heat causes ices to vaporize, dragging dust along, and the reflected sunlight from that escaping material makes the whole thing visible. So the mainstream interpretation, the one laid out in the preprints so far, is straightforward. 3I Atlas behaves like a comet. It likely has a rocky icy nucleus. It's venting gas. Everything we've seen fits comfortably within known comet physics. There's no necessity to invoke anything stranger. But then come the wilder takes. And this is where the conversation gets far more intriguing. Some independent analyses posted in less formal outlets or floated during media interviews have claimed mass estimates for 3I Atlas that reach into the tens of billions of tons. For perspective, that's several times heavier than a typical comet nucleus of the same supposed dimensions. A normal nucleus a few kilometers wide with density in the 500–1,000 kilograms per cubic meter range, roughly what you'd expect for a mixture of ice and rock, would weigh a few billion tons. To reach tens of billions, you'd need either a nucleus far larger than Hubble's upper estimate, or one that's far denser. If it's on the smaller end of that size range yet still that massive, then the material must be extremely dense, meaning metallic. And that's where the mention of nickel lines comes in. Some observers have reported possible nickel emission signatures within the coma. What does that mean, and what doesn't it mean? Nickel is indeed a metal, but finding it around comets isn't remotely unprecedented. Astronomers have routinely detected traces of metals such as iron, magnesium, sodium, and nickel in many cometary coma. The mechanism is simple. Comets contain dust grains rich in silicates and metal-bearing compounds. When solar radiation heats the nucleus, gas drag lifts those particles off the surface. Sunlight then heats and ionizes them, freeing individual metal atoms that emit their characteristic spectral line. Ground-based observatories, including the Very Large Telescope, have spotted nickel in several well-studied solar system comets, so the mere presence of nickel around 3I Atlas tells us nothing exotic. However, if those lines turned out to be unusually intense or the abundance ratios between metals and volatiles were off compared with standard comet chemistry, that would raise eyebrows. It could hint that the object formed under different chemical conditions, perhaps in another stellar system with a distinct metallicity, or even that it's a fragment from something that once underwent differentiation. Is when a planetary body melts internally, letting heavy elements sink toward its core. If such a planet or large asteroid were later shattered by an impact, you could end up with solid chunks of nearly pure metal drifting through space. We already have examples of this in our own solar system. Metallic meteorites, remnants of destroyed protoplanetary cores. Could 3I Atlas be an interstellar analogue of those? Not impossible, but very speculative without high-resolution spectroscopy confirming an anomalous makeup. Let's entertain possibilities anyway. If 3I Atlas truly were metal-rich, what plausible origins could produce it? One scenario, a fragment from a demolished exoplanet or large asteroid that once orbited another star, differentiated, then was blown apart, this piece flung into interstellar space. Another, though less likely, a solid chunk expelled from a supernova or stellar collision, surviving the violence somehow. And then there's the extreme hypothesis that it's manufactured, a derelict probe, a relic of some technology. To be absolutely clear, there is zero consensus supporting an artificial origin. Detecting nickel or deriving a high mass estimate does not equate to proof of engineering. Still, when multiple unknowns stack together, uncertain mass, questionable composition, plus the strange coincidence of a Mars window observation period overlapping a government shutdown, it's easy to see how speculation blossoms. Even without invoking technology, a dense metallic body racing through the inner solar system would be a huge deal. Aerospace and mining circles have long discussed capturing asteroids for their mineral value. An interstellar metal-rich visitor, even one we couldn't physically intercept, would be a once-in-a-lifetime opportunity for remote sensing and composition studies. That alone could justify heightened interest, possibly even attention from classified research branch. That's still conjecture, but informed conjecture. Now consider the human factor. A week of radio silence around something extraordinary is the perfect incubator for theories. People are wired to detect patterns, to connect. When official sources go quiet, imaginations rush to fill the vacuum. The shutdown created exactly that vacuum, and the ambiguity surrounding 3I Atlas's mass and makeup provided all the raw material for feverish speculation. These questions aren't irrational, They're what curiosity looks like under uncertainty. The trouble is, without solid data, some leap to conclusions faster than evidence allows. So how would we disprove the metal monster idea? Several straightforward ways. If further observations narrow the nuclear size and albedo so that its inferred mass drops into normal comet ranges, that ends it. If spectroscopy confirms ordinary ices and silicate dust, the metallic hypothesis collapses. If refined orbital modeling shows non-gravitational accelerations consistent with outgassing, that reinforces the standard comet model. If brightness variations match a porous, irregular body rather than a compact, dense one, same story. All these are measurable, they just require time and data. It's vital to remember that lack of evidence isn't evidence of mystery, it's simply evidence of what we don't yet know. We have no firm proof that 3I Atlas is mundane, and none that it's anything else. The current Hubble results fit a normal comet, but the uncertainties leave room for multiple interpretations. Its trajectory behaves like a lightly outgassing body, but could also match a denser object with mild venting. Scientifically, we're stuck in an awkward in-between, and that ambiguity, combined with the communication blackout during the Mars window week, keeps the narrative alive. If the object ultimately proves to be unusually massive or metal-rich, the implications are profound. It would suggest the interstellar population is far more varied than we've believed. Not just icy comets and rocky asteroids, but debris from shattered worlds, metallic cores, perhaps even remnants of engineered structure. That would reshape our picture of interstellar space, from a mostly empty void to a repository of cosmic wreckage. Or in the most speculative vision, a shipping lane, with lost travelers adrift between stars. But that's ahead of the evidence. The next phase depends on what post-shutdown data show: tighter mass constraints, clear chemical signatures, mundane orbital physics. Those results will determine which stories survive. Here's my commitment: when new findings drop, whether they validate or demolish the current theories, we'll revisit everything. The metal argument, the resource angle, even the artifact speculation, because that's how science moves forward, by confronting ideas with data, not dismissing them outright, but weighing belief in proportion to proof. At the moment, the proof is thin and the uncertainties vast. That's the honest state of play. And if you find that unsatisfying, welcome to the real rhythm of science. Slow, messy, indifferent to our impatience, yet relentless in its march toward clarity. Now it's time to examine how secrets, if any existed, could actually be contained. Because when data touch sensitive domains, the mechanisms of control matter as much as motives. Next, agency politics and classified operations. How information gets bottlenecked when government machinery grinds to a halt.
What the public perceives is that something extraordinary may have occurred in space while NASA remained silent. That silence, caused by procedural and legal constraints, leaves a vacuum, one that conspiracy theories eagerly fill. If something unexpected had indeed appeared during the Mars observation window, which chain of command would determine what information to release? That's the crucial question. If a NASA spacecraft detected an anomaly, the data would first go to the mission's science team. But if those scientists were furloughed during a government shutdown, who would actually be looking at the incoming data? The answer: the operations staff and flight controllers. Their job isn't scientific analysis, it's spacecraft health and safety. So if they saw something odd in a raw image, would they even know what it meant? And more importantly, would they have the authority to escalate it to the science team? Possibly, if it posed a threat to the spacecraft. But if it was simply intriguing and not mission critical, that data might just sit idle until the shutdown ended. Now, if the detection came through military sensors, the flow of information would take a very different path, through defense and intelligence channels. Those decisions are automatically classified. The public wouldn't hear about it unless there was a deliberate choice to declassify the material, which could take months or even years. Contrast that with the European Space Agency. Their observation campaign was openly announced, discussed, and documented. Space.com published pieces on September 28 and October 1, quoting scientists about their plans for observing the event. That's transparency in action. If NASA had similar plans, we didn't hear about them, not necessarily because they didn't exist, but because the shutdown halted the mechanisms that enable communication, the public affairs offices, press releases, and media briefing. So while scientists may have wanted to share information, they legally couldn't. The system simply went quiet. This brings us to the bigger picture: how internal friction and bureaucratic rules can distort public perception. NASA operates under strict legal limits during government shutdown. Operations can continue, but external communication cannot. Meanwhile, military and intelligence interfaces create data-sharing channels that are entirely opaque to the public. ESA's transparency, in contrast, made NASA's silence appear secretive, even when it may have been just procedural. If something unusual truly appeared, the decision on what to release would pass through multiple agencies, possibly including classified ones, slowing any public disclosure. None of this means something was deliberately concealed, but it does show how, even without bad intentions, information can be buried in bureaucratic fog. That's the unsettling part. Secrecy not born of conspiracy but of process. Fighting a conspiracy is one thing. Fighting bureaucracy is like trying to grab smoke. But there's still another layer to this. Who else might have been observing quietly, with advanced systems that don't make the news? Part 7. Alternate observers and black budget eyes. NASA and ESA aren't the only ones with eyes in the sky. To grasp the full scope, we need to map all the potential observers, because each could hold a piece of this cosmic puzzle. Publicly known missions are the obvious starting point. ESA's Mars Express and ExoMars Trace Gas Orbiter were active participants, as previously noted, but ESA also runs JUICE, the Jupiter Icy Moons Explorer, launched in April 2023. Still within the inner solar system, JUICE is on its way to a series of gravity assists. According to planning papers and early preprints, it could have had an opportunity to observe 3I Aeolus in November 2025, limited by its orientation and thermal constraints. That's after perihelion, but still scientifically valuable. Then there's China's Tianwen-1, orbiting Mars since early. While China's space program is far less transparent, Tianwen-1 is equipped with cameras capable of astronomical observation. Did they turn those cameras toward 3I Aeolus? We simply don't know. A lack of announcement doesn't mean it didn't happen. NASA's Psyche mission also enters this discussion. Launched in October 2023 to study the metallic asteroid 16 Psyche, its cruise trajectory might have allowed opportunistic imaging of 3I Aeolus. Several scientific papers mentioned the geometry as favorable for such a chance observation. Whether that opportunity was taken remains unconfirmed, but the idea is plausible. Now let's step into the shadows. The observers who don't publish data. Ground-based radar systems run by defense and intelligence agencies track countless objects in deep space. The most capable of these is the U.S. Space Force's Space Fence, an S-band radar located in the Marshall Islands. Though primarily meant for satellite and debris tracking, such systems can in principle detect objects much farther away if conditions allow. Could Space Fence have picked up 3I Aeolus? Technically possible, but highly improbable. The comet was tens of millions of kilometers away, far beyond typical radar range. Even powerful systems like Arecibo or Goldstone could only detect near-Earth asteroids a few million kilometers out. However, classified optical telescopes are another matter. The National Reconnaissance Office, NRO, operates high-resolution surveillance satellites comparable to or better than the Hubble Space Telescope. In fact, in 2012, the NRO famously donated 2 spare Hubble-class telescopes to NASA, proof of their advanced optics. Could such instruments have targeted 3I Aeolus? Possibly, but only if someone at a high enough level decided it was worth the effort. These satellites are tasked with strategic surveillance, not comet watching. Still, if the object triggered automated anomaly flags, data could exist classified inaccessible but real. Here's where speculation runs rampant. Online rumors have claimed that defense satellites detected unusual signatures, that emergency tasking orders were issued, that the data was immediately classified, yet no verifiable documents or whistleblower evidence support these claims. These remain stories built on could rather than did. I mention them only to show how such narratives spread, not because they hold evidentiary weight. Why wouldn't classified programs share their data publicly even if it contains something extraordinary? The reasons are simple and compelling. Capability protection. Revealing what your sensors can detect gives adversaries a roadmap to hide from them. Mission secrecy. Intelligence satellites aren't just classified for what they see, but for where and how they see. Lack of incentive. Satisfying public curiosity isn't their mandate, and there are many reasons not to release the data. This results in data asymmetry. ESA openly releases information. NASA will eventually do so post-shutdown, but military and intelligence even if they gathered data, we may never see it. That imbalance breeds suspicion, yet it's not necessarily deceit, it's just differing institutional priorities. Science, however, offers its own truth test. When ESA releases its datasets complete with timestamps and instrument metadata, and when NASA eventually does the same, we'll be able to cross-check their result. If both agencies observe the same object during overlapping timeframes, their data on position, brightness and spectral composition should align. If they diverge drastically, that's when eyebrows should rise. The same applies to orbital data published by the Minor Planet Center, MP. Their publicly available orbital solutions are compiled from worldwide observations. If NASA's Mars orbiters contributed data that shifted the orbital fit, we'll see it. If not, that absence itself is telling but still procedural, not necessarily One more misconception worth clearing up. NASA's HiRISE camera aboard Mars Reconnaissance Orbiter. Some speculate it could have resolved fine details, perhaps artificial structures on the comet's surface. The math doesn't hold up. HiRISE's maximum resolution from Mars orbit is about 30 centimeters per pixel. At 30 million kilometers away, that becomes roughly 30 kilometers per pixel, far too coarse to resolve any structure at all. You can measure overall brightness and perhaps detect shape changes, but not individual features or engines. When the ESA and NASA datasets become public, their combined analysis will provide the clearest test of transparency. If everything aligns, spectra, brightness, orbital data, it suggests no suppression or anomaly. If it doesn't, that's when the questions become legitimate. Until then, we rely on open data, track what's trackable, and note the gap. Part 8. The Mars Proximity Effect. Hidden opportunities and subtle influences. When an interstellar object passes within 30 million kilometers of a planet, even without direct contact, subtle interactions can occur, not cataclysmic, but potentially reveal. First, the physics. Mars's gravity, though weak at that distance, still exerts a measurable influence. A slight gravitational tug could alter 3I Elitzelus's trajectory just enough for precision instruments to detect. Such deflection helps refine orbital models. A small but scientifically valuable event. Then comes the Martian space environment. Mars has a thin, extended exosphere and remnants of a once active magnetic field. The planet interacts continuously with the solar wind, creating a magnetotail and bow shock region. While 3I Elitzelus was too distant to pass through these regions, the concept is instructive. A comet passing closer might experience plasma interactions, distortions in its tail, ion deflection or temporary brightness. ESA's Mars Express carries instruments like the high-resolution stereo camera, HRSC for wide-angle imaging, and NOMAD, a spectrometer capable of analyzing atmospheric or cometary gases. These could detect variations in gas output or compositional shifts, offering clues about 3I Elitzelus's activity. What could they find? Sudden brightening from dust or gas outbursts, changes in molecular signatures, suggesting volatile release, shifts in coma symmetry hinting at jet activity. Comet outbursts are natural, often caused by solar heating, sudden ice exposure or surface collapse. Detecting one during the Mars window would be exciting, but not extraordinary. Solar activity adds another layer. The solar wind isn't steady. Coronal mass ejections, CMEs, send waves of charged particles through space. A CME hitting 3I Elitzelus near the Mars window could cause a temporary surge in brightness, perfectly explainable by increased solar particle flux. Historical data from ESO or stereo could confirm whether such an event occurred during that period. Finally, a speculative thought. Could any Mars orbiter have intercepted particles from the comet's tail? The dust from 3I Elitzelus spreads over millions of kilometers, composed of micron-sized grain. Though improbable at 30 million kilometers, the theoretical possibility of particle detection through instruments sensitive to micrometeoroids remains scientifically fascinating. These physical interactions, however small, represent natural laboratories. Even if no mysteries emerge, The data gathered from such encounters help us understand how interstellar visitors behave under planetary influence, a rare opportunity for science, not secrecy.
At a distance of around 30 million kilometers, the density of particles surrounding the object would still be extremely sparse, yet not entirely absent. If a spacecraft happened to cross paths with the outermost wisps of the coma, or tail, and if that probe carried equipment designed to sense or trap dust, it might collect a handful of grains. This is precisely the technique used by NASA's Stardust mission, which deliberately plunged through a comet's diffuse atmosphere to harvest samples. Mars orbiters, however, were never built with that type of operation in mind. While they do present physical surfaces capable of being hit by particles, they lack specialized collectors. In theory, some dust could have stuck to them, but retrieving and analyzing it would be another challenge altogether. Holding in one's hands material from an interstellar body would be a monumental achievement. Of course, that scenario never unfolded. The angles were off, the particle density was far too low, and none of the orbiters around Mars possess any sort of sample return hardware. Still, it's an intriguing mental exercise in what might one day be technically feasible. Consider MAVEN, the Mars Atmosphere and Volatile Evolution mission. It's primarily tuned to study the solar wind and the upper layers of the Martian atmosphere. Its instrument suite measures things like charged particle properties, magnetic fields, and energetic plasma. If conditions in the solar wind shifted during the window when the comet passed near Mars, MAVEN would have seen those changes. In principle, the spacecraft could even detect some secondary effect of the comet, perhaps ions released from the coma streaming through interplanetary space and subtly disturbing Mars's surrounding plasma environment. But to be honest, that scenario veers into speculation. At tens of millions of kilometers, any such disturbance would likely be so minuscule as to be undetectable. Still, MAVEN's data can provide valuable context on the space weather conditions during the encounter. If sometime later scientists cross-reference MAVEN measurements with cometary activity, those comparisons could form the basis of interesting papers on large-scale solar system interactions. Yet the scientific consensus leans toward the mundane. Nothing extraordinary was expected. Comets making close approaches to Mars aren't unheard of, although interstellar visitors are rare. Physics predicts nothing dramatic at 30 million kilometers. The most realistic outcome is that the comet stayed on its course, outgassing as usual, while Mars orbiters gathered images and spectra. When the data becomes public, it should show an ordinary comet behaving in an ordinary way. Should it reveal something else entirely, then things get interesting. But leaping to extraordinary conclusions before examining the evidence is premature. This brings up an important cautionary note. Humans are superb pattern recognition machines. A small dip or bump in a light curve can easily tempt an observer into thinking something profound has occurred. Maybe the nucleus rotated to bring a brighter region into view. Maybe there was a minor outburst. Or maybe it's just measurement noise. Until the underlying cause is understood, a wiggle is just a wiggle, not proof of spacecraft maneuvers or technological signatures. This is precisely why peer review exists. Scientists stress test interpretations and exhaust alternative explanations before making claims. The public, understandably, tends to be less patient. When speculation fills the gap left by silence, every minor deviation begins to look like a signal. I've promised to revisit this topic once post-conjunction analyses are released. If NASA or ESA researchers publish studies of what their Mars-orbiting instruments saw, I'll go through them. If brightness changes, spectral quirks or other unusual findings emerge, they'll appear in the peer-reviewed literature, and if the comet turns out to be unremarkable, we'll know that too. In this context, boring can actually be comforting. It would mean nature is behaving as our models predict, and yet this leads to a more unsettling question. Suppose there really were secrets. How could anyone hide a genuine cosmic discovery from a worldwide network of scientists and an increasingly skeptical public? That's where so-called silencing mechanisms enter the conversation. Part N. Silencing mechanisms. How would you bury a space mystery? If someone wanted to suppress information about 3I Atlas, what would that look like? Not in a Hollywood thriller with men in black confiscating hard drives, but in the real world, where bureaucracy and plausible deniability act as the tools of choice. Let's step through the actual mechanisms that produce silence, from perfectly legal ones to more questionable possibilities. First up, shutdown rules. These are real, powerful, and well documented. During a US government shutdown, NASA's public affairs operations grind to a halt. Websites don't update, not because someone gave a gag order, but because the staff who maintain them are on furlough and legally forbidden to work. Press releases vanish because no one is on duty to write them. Social media accounts go dark because no one's there to post. This is procedural silence, not intentional suppression, but the end result is identical. The public hears nothing. Crucially, this silence is predictable and codified in NASA's continuity plan. So if you were someone hoping certain facts stayed quiet, a shutdown would be extremely convenient. You wouldn't need to order secrecy, just let normal procedure run its course. Now it's essential to separate two often confused ideas: embargo versus classification. A scientific embargo is when researchers voluntarily agree to hold back results until a coordinated release date, usually to coincide with publication in a journal. It's a standard practice meant to preserve the integrity of peer review and avoid piecemeal leaks that fuel misinterpretation. Embargoes are temporary and voluntary. Classification, on the other hand, is a legal status. Classified material is shielded by law from unauthorized disclosure, and violating that restriction can lead to criminal charge. Classification authority usually comes from the executive branch under a national security rationale, with levels like confidential, secret, and top secret. It dictates how data must be stored and who can access it. These are not interchangeable. An embargo is professional courtesy. Classification makes disclosure a crime. Don't conflate the two. Have we seen delays in NASA data during previous shutdowns? Absolutely. Every time the government shutters, the data pipelines slow or stop. Mars rover images that normally appear online within days can sit in a backlog. Hubble releases are postponed. Mission web pages freeze. This is all documented. The 2018-2019 shutdown lasted 35 days and triggered widespread delays across multiple missions. Scientists publicly voiced frustration over lost productivity and postponed publications. This is normal. So if data from 3I Atlas ends up delayed, that fits the pattern. It's not automatically evidence of special handling, but here's where it gets more subtle. Format barrier. Most people don't realize that raw astronomical data isn't just JPEGs you can pop open in a browser. It's typically stored in specialized formats like FITS, Flexible Image Transport System. These files are huge and include not just pixel arrays, but also extensive metadata, instrument settings, calibration parameters, timestamps, pointing coordinates. Analyzing them requires specialized software and deep familiarity with the instrument. Without understanding noise sources, calibration quirks, and processing pipelines, you can't draw reliable conclusions. So even if NASA were to dump every raw file online tomorrow, the vast majority of the public wouldn't know what to do with it. This isn't sinister, it's simply the technical reality of modern astronomy. But it does mean that open data isn't truly accessible in practice without expertise. Then there's compartmentalization, a real phenomenon inside any sprawling organization, especially in government or research institutions with sensitive work. Different teams handle different pieces of a project. In intelligence agencies, this is deliberate, a safeguard against leaks. In civilian science, it happens naturally as a byproduct of specialization. The engineers operating a spacecraft aren't the same people running orbital dynamics models, who aren't the same people performing spectroscopic analysis. If something odd appeared in one dataset, the first person to see it might not even recognize its significance. They'd note it, perhaps flag it for a specialist, but that information might not flow quickly, particularly during a shutdown, when staff are furloughed and internal communication slows to a crawl. This creates a plausible scenario where unusual data exists, someone glimpses it, but the expert who could interpret it isn't working, and the clue never gets properly flagged. That's not conspiracy, it's organizational friction. Real evidence of deliberate suppression would look entirely different. Actual emails, memos, logs, or whistleblower statements with names, dates, and verifiable details. As of early October 2025, nothing of that sort has surfaced regarding 3I Atlas. No leaked documents, no insider testimony. That absence is telling. In today's environment of ubiquitous digital communication and widespread distrust of authorities, genuine secrets are notoriously difficult to keep. Classified programs, Pentagon UFO memos, intelligence missteps, they all leak eventually. If there were a true smoking gun about 3I Atlas, chances are someone would have spilled it by now. That doesn't prove nothing's being hidden. It could mean the circle of knowledge is extremely small, or that leaks simply take time. But until verifiable evidence emerges, speculation remains just that, speculation. So what can you as an interested observer do once the data begins to flow? Here's a simple skeptic's toolkit. First, check file integrity. FITS files include checksums, mathematical fingerprints that reveal if a file's been altered since creation. Second, examine timestamps. Observations should line up with the predicted viewing window. If an image is dated at a time when the comet wasn't even visible from that spacecraft's location, something's off. Third, scrutinize the instrument housekeeping data that accompanies each observation: spacecraft status, pointing direction, temperature, power level. Oddities there can hint whether an observation was routine or out of the ordinary. Fourth, cross-check between missions. If NASA and ESA both collected data during overlapping periods, their results should align. Discrepancies need explanation. This isn't paranoia, it's simply the practice of good science. Trust, but verify. A large-scale cover-up spanning ESA, NASA and the Minor Planet Center would leave telltale fingerprints. The comet's orbit is determined by fitting models to observations from multiple sites over time. If some data were withheld or falsified, the orbital fit would degrade, producing larger residuals. Amateur astronomers around the world are also tracking 3I Atlas and contributing their observations to the MP. If the official orbital solutions didn't match the amateur data, that mismatch would be obvious. The MPC even publishes residuals, so anyone can see how well the model fits each observation. Pulling off a conspiracy here would require synchronized cooperation across multiple nations, agencies and independent observers, a highly implausible feat. The old saying goes that information wants to be free. In science, that impulse is even stronger, because reputations are built on transparency and discovery. So it's worth reiterating, silence does not automatically equal suppression, yet to the public eye it looks suspicious. When official channels go quiet during a potentially extraordinary event, people jump to conclusions. That's human nature. It's exactly this instinct, the craving for mystery, that gives stories like this their allure. We want the shutdown to signify something deeper than budget politics. We want the comet to be extraordinary because ordinary is dull. I'm not immune to that impulse either, none of us are. But wanting doesn't make it true, evidence does. And at this point, evidence for an active cover-up of 3I Atlas is thin to non-existent. What we're seeing is procedural silence, technical hurdles and organizational bottlenecks. Real but unremarkable. The real question is whether those ordinary explanations are sufficient, or whether something extraordinary is hiding in the gap. To get closer to an answer, let's lay out the competing scenarios and see which survive careful testing. Part 10. 6 Competing Hypotheses. Time to impose some order on the chaos. Here are 6 different ways to interpret what did or didn't happen during the Mars window in early October. For each, I'll outline the core claim, the evidence supporting it, and crucially what would falsify it. Because a claim that can't be disproven isn't science at all, it's just a story. Hypothesis 1. Bureaucratic coincidence. The simplest explanation is that the shutdown explains the communications gap. NASA's Mars assets either didn't observe the comet, or they did and the data is just sitting in a backlog awaiting post-shutdown processing. ESA proceeded with its campaign as announced. The comet acted like a comet. When all the data finally emerges, it will all line up. This is the null hypothesis, the boring one. It requires no conspiracies, no exotic physics. It fits with how shutdowns work and how science typically unfolds. Supporting evidence includes NASA's own continuity plan, stating communications, pause during funding lapses, ESA's transparent discussion of its observing plans, and the absence of verified leaks or whistleblower claims. How could this hypothesis be falsified? If ESA releases data and the Minor Planet Center updates orbital elements, and those updates deviate significantly from prior predictions, that's a red flag. If NASA's eventual data shows the comet in locations or states inconsistent with ESA's observations during the same time windows, that's another problem. If amateur observers independently report brightness or positional anomalies absent from official datasets, that hints at selective reporting. The key test is consistency. If public and private observations all match, Hypothesis 1 stands. Hypothesis 2. Massive metallic core. Under this idea, 3I Atlas has a nucleus on the large end of the size range, an unusually high density,
possibly rich in metal. That would put its mass at the extreme upper estimates, tens of billions of tons. Stronger than usual nickel emission lines in the coma might indicate enrichment in metals, compared to the icy rocky mixtures of ordinary comets. This is speculative, but not impossible. We know metal-rich asteroids exist in our own solar system. A fragment of a differentiated body from another star could plausibly travel into interstellar space. Supporting evidence, such as it is, comes from early reports and blog posts, especially those amplified by avian outlets like the Debrief, highlighting unusual mass-to-size ratios and possible nickel detections. The problem is these aren't peer-reviewed results. They're preliminary, often based on incomplete data or aggressive interpretations. What would falsify this hypothesis? More precise constraints on the nucleus's size and albedo that bring mass estimates down to ordinary cometary values. Spectroscopy showing a composition dominated by water ice, carbon monoxide and silicate dust, with metal abundances matching solar system comets. Non-gravitational acceleration parameters, consistent with volatile outgassing, rather than inert high-mass behavior. If the light curve shows rapid variations, indicative of a fluffy, irregular, low-density tumbling body, that also argues against a dense metallic core. The post-perihelion data will be key. If brightness and activity continue behaving like a normal comet through perihelion and beyond, the metal core hypothesis loses momentum. Hypothesis 3, engineered or technological artifact. This is the headline grabber. The idea that 3I Atlas isn't natural at all, that it's a probe, a derelict craft, or some fragment of alien technology. Evidence for such a claim would include non-gravitational maneuvers that can't be explained by outgassing, light curves showing geometrically structured rather than chaotic rotation, spectral signatures inconsistent with any known comet or asteroid materials, or narrowband radio emissions coherent enough to stand out from natural background noise. At present, no verified evidence supports this scenario.
None of the peer-reviewed literature presents any claim that 3I Atlas is artificial. There are no confirmed signal detections. There are no orbital behaviors that demand an explanation outside of natural processes. Most of the speculation around artificiality arises from the curiosity sparked by Umar Ma and the fact that 3I Atlas is now the next highly visible interstellar visitor. Some voices, like Evie's, advocate for keeping the possibility on the table, which is reasonable in principle, but extraordinary claims necessitate extraordinary evidence. How would you disprove this idea? You'd need to show that the orbital residuals follow a smooth trajectory consistent with cometary outgassing. You'd need light curves that align with the rotation of a naturally irregular body. Spectra would have to reveal conventional dust and gas composition. Radio observations would need to return only background noise or naturally occurring emissions. If all of these lines of inquiry consistently align with what's expected from a comet, then the artificial artifact hypothesis collapses. The onus of proof rests on those asserting artificiality, not on the broader scientific community to disprove it. The falsification criteria, however, are straightforward. Natural explanations must fail before artificial explanations are entertained. Hypothesis 4, which I'll call third-party intervention, envisions a scenario in which some external actor, likely a state with advanced space capabilities, conducted a covert intercept, rendezvous or inspection of 3I Atlas during the Mars window. Possible motives could include reconnaissance, sample collection, or even nudging its trajectory. This remains highly speculative, bordering on science fiction given present technological limits, but it's worth outline. Evidence would include sudden, unexplained orbital maneuvers inconsistent with outgassing predictions, sightings by amateur observers of unknown spacecraft near the comet, leaked communications or whistleblower accounts from space agency insiders. At present, none of this exists publicly. Orbital solutions show no anomalous deviations. There have been no credible leaks, and amateur monitoring has been continuous and unremarkable. How could you falsify this hypothesis?
by demonstrating that orbital fits from multiple agencies remain consistent over time, by showing that all observed positional and velocity data are fully explained by solar gravity and known non-gravitational forces. Absence of Doppler anomalies and corroboration from independent observations would also disprove it. Additionally, consider the technological question. Does any nation have the capability to intercept an object moving at tens of kilometers per second, 30 million kilometers away, over a one-week observational window? The answer is almost certainly no. To maintain this hypothesis, one would require not only a cover-up, but also an unacknowledged space capability far beyond what is publicly known, a formidable and unlikely scenario. Hypothesis 5 involves classified observation. This posits that military or intelligence assets monitored 3I Atlas during the Mars window, collecting data that is now restricted or siloed. The data may exist and even be scientifically interesting, yet it isn't shared with civilian scientists or the public. Future leaks or eventual declassification might reveal it, or it could remain hidden indefinitely. By its nature, this hypothesis is difficult to falsify since classified information cannot be verified publicly. Indirect indicators would include former insiders hinting at observations, FOIA requests denied under national security exemptions, or operational documents referencing the comet in a classified context. None of these have surfaced openly. How could you challenge this hypothesis? You can't directly access the classified data, but you can evaluate consistency in the public record. If publicly available civilian data is comprehensive and aligns across multiple observers, the argument for hidden classified observations weak. Conversely, unexplained gaps or discrepancies that only classified data could clarify keep this idea alive. Ultimately, the practical test is whether public scientific records can stand on their own. Hypothesis 6 considers a planetary interaction event. Perhaps 3I Atlas's close pass by Mars coincided with transient phenomena induced by the surrounding space environment. This could include solar wind gusts, coronal mass ejections, or interactions with Mars's weak magnetosphere, resulting in temporary brightening, coma asymmetries, or spectral variations. Such events are scientifically intriguing but remain consistent with natural processing. Supporting evidence would consist of contemporaneous space weather data, showing enhanced solar activity, MAVEN measurements of disturbances in the Martian space environment, and observed brightness or activity spikes in the comet during the same window. This hypothesis is both testable and falsifiable. If space weather records show no anomalies and the comet exhibits no unusual behavior, the hypothesis is weakened. If both the comet and Mars's environment display coordinated deviations, it gains support. This is exactly the kind of measurable, analyzable science that can advance our understanding of comet plasma interactions. For each hypothesis, I've outlined expected signatures, the types of supporting data, and the means of falsification. Who can test these ideas? ESA's Mars Express and ExoMars teams will provide imaging and spectroscopy to directly assess hypotheses 1, 2, and 6. Orbital dynamics experts at the Minor Planet Center and JPL will refine the comet's trajectory. Ground-based observatories, Hubble, and potentially JWST, can supply post-perihelion observations relevant to hypotheses 3 and 4. Amateur networks provide independent cross-checks, indirectly testing hypothesis 5. The scientific process, though often slow and bureaucratic, will eventually deliver answers. Timing is critical. Perihelion occurs around October 29–30, 2020. Post-conjunction observations from Earth begin in late November through December, when ground-based telescopes can see the comet again after it emerges from the sun's glare. These observations will provide independent verification of any claims or suspicions generated during the Mars window. If the comet's brightness, activity, and trajectory in December match pre-existing predictions, that strongly supports hypothesis 1. Unexpected deviations keep alternative hypotheses viable. It's important to note that hypothesis 1, bureaucratic coincidence, is the most parsimonious. It requires the fewest assumptions and aligns most closely with established facts. This doesn't automatically make it correct, but it provides a logical starting point. Occam's razor suggests avoiding unnecessary complexity. Don't invoke conspiracies when procedural delay suffices. or alien technology when a comet explains the data. Yet parsimony is not certainty. Evidence remains the guiding principle. If observations demand a more exotic explanation, science will follow, just as it did with Oumuamua, where the artifact hypothesis was seriously considered before natural explanations prevailed. Currently we have 6 hypotheses ranked roughly by plausibility based on available evidence. Hypothesis 1 leads, followed by 6 and 2 as scientifically interesting alternatives. Hypothesis 5 is unfalsifiable but plausible considering classified systems. Hypothesis 3 and 4 are long shots, lacking any supporting evidence. All remain at least partially testable through incoming data. This keeps the narrative compelling. Speculation is bounded by measurable reality. The cosmos doesn't easily conceal information. Light travels, trajectories endure, and instruments. Once 3I Atlas re-emerges from behind the sun, once the shutdown ends, and data is released, and once scientists and amateurs cross-check observations, answers will emerge. Maybe not all answers immediately, but enough to distinguish fact from conjecture. Which brings us to the post-conjunction window and the recovery of truth. Part 11. Post-conjunction reappearance and data collection. Mark the calendar. Late November through December 2025 is when 3I Atlas will become observable from Earth. After its solar conjunction, the comet will have passed perihelion around October 29-30, undergone maximum solar heating, and either behaved as expected or revealed something unusual. By the time it's visible again, weeks will have elapsed. Escaping gases, dispersed dust, and any minor trajectory shifts from non-gravitational forces will all be evident. Observations in December represent the cosmic record of events during the dead zone. Ground-based telescopes will without question target the comet if it remains sufficiently bright. Its apparent magnitude will indicate ongoing activity. Some comets brighten gradually toward perihelion and then fade quickly. Others remain active for extended periods. We won't know which type 3I Atlas is until we observe it. Hubble and JWST may also provide data, depending on scheduling and approved target of opportunity time, which interstellar visitors easily justify. JWST's infrared capabilities are particularly useful for examining the nucleus and characterizing dust composition. Even ESA's JUICE mission may contribute. During its inner solar system cruise toward Jupiter, instruments can observe opportunistic targets including 3I Atlas, if thermal and geometric constraints allow. These observations provide a unique vantage point, enabling parallax measurements and cross-validation with Earth-based data. Post-conjunction, 3 priorities dominate: refining the orbit, obtaining high-resolution spectroscopy, and tracking photometry light curves. Extended observations spanning July through post-perihelion December will refine orbital elements, clarify non-gravitational effects, and enhance prediction accuracy. Spectroscopy will identify gas composition, detect volatiles, and assess potential metallic components, directly testing hypothesis 2. Photometry over hours and days captures rotation, brightness changes, and activity trends. Any unusual brightening or erratic variability would be noteworthy. Data rescue is critical. Community efforts to archive and cross-check observations safeguard against loss. When official NASA or ESA data is released, redundant backups, time-stamped archiving, and distributed storage are essential. Comparative spreadsheets capturing date, time, observer, instrument, position, and magnitude are invaluable for identifying anomalies. Outliers might indicate errors or genuine anomalies, requiring careful investigation. Manage expectations. Science releases lag observations due to calibration, analysis, and peer review. Shutdowns exacerbate delays. NASA may release Mars data months after collection. This is operational friction, not evidence of malfeasance. Consistency in released data, compared across time periods, provides a check. Unusual gaps or degraded quality specific to key observation dates would warrant attention. What constitutes a smoking gun versus normal behavior? Smoking guns would include structured changes inconsistent with natural outgassing, unusual molecules like industrial pollutants, refined metals, or orbital residuals that cannot be reconciled with gravity and cometary physics. Normal behavior aligns with decades of comet observations: perihelion brightening, predictable dust and gas production, irregular light curves from rotation,
and an orbit consistent with minor non-gravitational terms. Following the Minor Planet Center's electronic circulars, MPEX is recommended. They report observations, orbital updates, and discoveries for 3I Atlas, C2025N1, track updates, eccentricity changes and non-gravitational parameter shifts. Mars Express and ExoMars archives provide further data, timestamps and metadata, confirm observation timing and quality. Post-perihelion spectra, revisiting metal abundance claims will offer additional verification. Consistent reports across multiple observatories indicate reliable results. Discrepancies hint at calibration errors or false positives. Replication is essential. 1 measurement is suggestive, 3 measurements indicate evidence, 10 establish fact. Reassuringly, NASA's shutdown is legally constrained, not a ban on science. Spacecraft continue operations, only public communications and non-essential planning halt. Data collection continues, with backlogs processed post-shutdown. There is no reason to believe deliberate destruction or indefinite withholding of data occurs absent evidence. The post-conjunction window offers the second observational opportunity, December, with clear skies and restored funding. Miss this window and 3I Atlas fades as it recedes from the Sun, leaving only the most capable telescopes able to track it. Interstellar visitors operate on their schedules. We must maximize observation while they remain accessible. Watch the skies, monitor released data, and let facts supplant speculation. Perhaps though the most profound secrets won't emerge from new data at all.
Perhaps the clues are already sitting in archives we've had for years but simply haven't examined closely enough. Let's explore legacy missions and the potential secrets they might conceal. Part 12, Digging into Legacy Missions for Hidden Hints. Picture this. What if evidence about 3I Atlas has been quietly present in data we've held all along, tucked away in mission archives? Space missions generate immense volumes of data, far more than can ever be analyzed in real time. Instruments record countless frames, sensors log endless streams, and files accumulate in databases. Years later, a diligent researcher revisits the data for a specific target, and suddenly, an object pops up in the background of a photo that no one noticed at the time. This is real. It's called a precovery or serendipitous detection, and it has extended the observational histories of numerous comets and asteroids, including 3I Atlas. The Minor Planet Center lists the discovery date as July 1, 2025. But that doesn't preclude earlier observations. Precovery images are snapshots or measurements taken prior to official discovery, often by surveys aimed at entirely different regions of the sky. If 3I Atlas happened to appear in archival data from months or even years before July, those observations could dramatically extend the orbit baseline, sharpening our understanding of its path. Finding them isn't trivial. You must work backwards from the current orbit to predict where the comet was at previous times, then comb through archives of observatories that may have imaged that region. It's painstaking but entirely feasible, and amateur astronomers contribute to this process regularly. Mars orbiter datasets offer another promising avenue. Mars missions capture thousands of images, while most target the planet itself. Some are calibration shots, dark frames, or wide-angle sky images used to check instrument performance. If a Mars spacecraft inadvertently captured a field containing 3I Atlas even faintly, it would be valuable data. The likelihood is low. After all, the comet is small and faint, but not impossible. Crowdsourcing such a search could yield release pointing logs, share metadata, and let a community of citizen scientists comb the archives. Citizen science has discovered exoplanets, classified galaxies, and even spotted supernovae. It could very well find a comet. To set context for what qualifies as unusual, let's recall past interstellar visitors. The first, Oumuamua, was strange, elongated, lacking a visible coma, and displaying non-gravitational acceleration that outgassing models could not explain. These anomalies fueled speculation about artificial origins. Borisov, the second visitor, was mundane in comparison. It looked and acted like a conventional comet, with compositions aligning with what we expect from solar system objects. No one suggested artificiality for Borisov. 3I Atlas falls somewhere in the middle. It possesses a coma, shows comet-like activity, but uncertainties in mass and composition leave room for curiosity. By benchmarking against Oumuamua and Borisov, we can calibrate our expectation. If 3I Atlas resembles Borisov, the outcome is scientifically interesting yet natural. If it exhibits features more like Oumuamua's unexplained traits, questions deepen. Searching Hubble and ground-based archives for precoveries is conceptually straightforward. Hubble's archive is public and searchable by sky coordinates and date ranges. If it imaged the region where 3I Atlas later appeared, those images could contain the comet. Ground-based surveys Pan-STARRS, Catalina Sky Survey, or ZTF, cover wide sky areas repeatedly, with archives stretching back years. Systematic searches at predicted past positions could yield detections, each one extending the orbital arc and refining the comet's trajectory. The Minor Planet Center tracks and encourages such efforts, listing pre-discovery observations once verified. For 3I Atlas, a few precovery observations from late June 2025 have already been logged, but earlier images may still await discovery. Here's a wildcard. IBEX and Voyage, NASA's Interstellar Boundary Explorer, launched in 2008, maps energetic neutral atoms at the heliosphere's edge. Voyager 1 and 2, now in interstellar space, monitor plasma, cosmic rays and magnetic fields. Could these missions have picked up signals from 3I Atlas? Almost certainly not directly. The comet never passed near them, and they aren't designed to image inner solar system objects. However, if 3I Atlas interacted unusually with the solar wind, or emitted unexpected particles, secondary effects might have been detected by their instrument. This is highly speculative but worth noting when exhausting all possibilities. Amateur astronomers who observed 3I Atlas in July and August are invaluable. Photometric and astrometric measurements from dozens of amateurs worldwide were submitted to the Minor Planet Center. These independent data points provide redundancy and cross-verification. Comparing amateur data with professional observations can ensure no selective reporting occurred. Any discrepancies, variations in brightness or positional data, merit careful attention. The amateur community's attentiveness means anomalies, if visible, are often noted in forums or mailing lists. Aligning amateur photometry with Hubble measurements provides a critical cross-check. Differences should be explainable through filter differences, seeing conditions or calibration methods. If not, they could signal either observational errors or genuine cometary behavior, such as outbursts. A roadmap for community engagement is clear. Identify time ranges for potential precoveries, from the comet's probable entry into the planetary region, months or years prior to discovery. Pinpoint instruments capable of detecting faint objects, including Hubble, ground surveys, and perhaps all sky cameras designed for meteor observation. Calculate predicted past positions and search those fields. Submissions go through the Minor Planet Center, vetted and incorporated into the official record if validated. Even negative results have value. They constrain models, set brightness limits, and define activity levels, refining our understanding even without discoveries. This approach democratizes the investigation, countering perceptions that data is withheld or lost. The more eyes on the archives, the more robust and transparent the conclusions. When ESA and NASA release Mars window data, rapid integration, cross-referencing with amateur observations, and careful inspection of timestamps, instrument modes, and metadata ensure accountability. Discrepancies warrant documentation and explanation. This is rigorous scientific scrutiny, not paranoia. Legacy data, coupled with community effort, can bridge gaps left by official channels. Anyone with access and interest can engage. Archival exploration is science in action. But before moving on, we confront the most speculative idea. What if a signal exists, and we've overlooked it? Part 13. Signals, Communication and Contact Hypothesis. Let's be explicit. This is highly speculative. The notion that 3I Atlas could host artificial signals or act as a relay lacks verified evidence. No confirmed detections, peer-reviewed claims, or official SETI announcements exist. Yet the conversation persists, fueled by online discussion and the lingering intrigue from Oumuamua. We can, however, frame a legitimate investigation of potential signals. A plausible artificial signal would likely be electromagnetic,
radio or optical propagating effectively through space. It would probably be narrowband, concentrated at a single frequency, contrasting with natural sources, which emit broadband noise. Artificial transmitters, at least as humanity builds them, focus power efficiently, akin to a radio station compared with static. The signal would also exhibit Doppler drift matching the comet's motion. As 3I Atlas approaches or recedes from Earth, the radial velocity changes, shifting the observed frequency. A signal consistent with predicted Doppler drift would strongly hint at an origin tied to the comet. Detecting such a signal is challenging. During the Mars window, 3I Atlas was tens of millions of kilometers away. Signal strength drops with distance squared, necessitating extremely sensitive receiver. The world's largest radio telescopes, the FAST in China, or the VLA in New Mexico, have the requisite sensitivity, but must be precisely aimed at the right time. Rapid Doppler shifts, hundreds to thousands of hertz per second depending on frequency, add complexity. Specialized software can track this, a standard but computationally intensive SETI task. Radio frequency interference complicates matters further. Earth-based signals from satellites, radars or electronics can mimic extraterrestrial sources. A real signal must appear when pointing at the comet, disappear when pointed away, and reappear consistently when retargeted. Public discourse, amplified by media coverage and online discussion, has tied nickel and mass claims to engineered hypotheses. Projects like Lowe's privately funded Galileo search, exploring technological signatures from anomalous objects, operate at the edge of legitimate inquiry, but media often overstates the implications. Nickel alone does not indicate engineering, it occurs naturally. High mass estimates, even if unusual, don't prove technology. Multiple independent evidence lines are required to seriously consider artificiality. For motivated amateurs, radio telescopes exist that can attempt such observation. While less sensitive than professional instruments, they can detect strong signals. Software-defined radios, SDRs paired with antennas and signal analysis software, can record dynamic spectra, frequency versus time representation. Observers could monitor 3I Atlas for signals at consistent frequencies, exhibiting Doppler drift in sync with comet motion, and ideally repeatable across multiple sites. Raw time-stamped recordings, shared across observers, would allow verification. Multiple independent detections are compelling. A single sighting is only a curiosity. The default assumption, the null hypothesis, is that 3I Atlas is a comet. Comets emit broadband thermal radiation from dust, and ultraviolet or visible light from gas fluorescence, not narrowband radio signals. Non-detections are expected but don't definitively rule out technology. Coordinated post-conjunction observing windows, organized by amateur and SETI communities, would maximize chance. The signal should originate from the comet's predicted ephemeris, show Doppler drift consistent with radial velocity, and display temporal structure pulses or modulation, rather than a static carrier, though a carrier remains possible. Information encoding would provide definitive proof, though decoding is a separate challenge. Testability is critical. Any claim of a signal must include frequency, bandwidth, drift rate, observation time, equipment used, raw data files, and control observation. Extraordinary claims demand extraordinary evidence, and replicability is essential. Curiosity about potential artificiality is reasonable. The universe is vast, and advanced civilizations could in principle leverage interstellar objects. But improbable claims need strong proof, which currently doesn't exist. The rational stance is curiosity tempered by skepticism. Search, observe, listen, but do not conclude without data. Should compelling evidence arise, it must undergo rigorous scrutiny before accepting. Even without detecting alien beacons or probes, 3I Atlas has sparked meaningful discussions. Its passage pushes scientific curiosity, prompts policy considerations, and demonstrates the value of observation, community engagement, and rigorous analysis.
Part 14. The broader impact on interstellar object science and policy. Let's pause for a moment and take the straightforward assumption at face value. 3I Atlas really is nothing more than what its data suggests. A natural comet, a frozen wanderer, ejected from another star system, now slicing through our solar neighborhood. before slipping back into deep interstellar space. Even if that's the entire story, no hidden craft, no secret transmissions, the implications are still immense. This single visitor, with its activity, its silence, and its sudden appearance, has already begun reshaping how we think about interstellar science, how missions are planned, and how agencies communicate during moments of uncertainty. The ripple effects have less to do with extraterrestrials or conspiracies, and far more to do with readiness, transparency, and the fragility of the systems we depend on to watch the sky. Let's begin with the science. 3I Atlas represents the third confirmed interstellar object to be identified. The first was the elongated enigma Oumuamua in 2017. The second was the comet-like 2I Borisov in 2019. 3 objects in just 8 years, hardly a torrent, but enough to establish a trend. The galaxy is not an empty void. It is, in fact, bustling with fragments of alien worlds, blocks of ice and stone expelled from distant planetary nurseries, now drifting between stars. Models suggest thousands of such interstellar objects sweep through the inner solar system annually. Most are too dim, too small, or pass too far to ever notice. What we are seeing are only the giants, the bright stragglers, whose paths take them close enough to the Sun or Earth to catch the sweep of our survey. 3I Atlas was detected by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, on July 1st. This ground-based robotic network was built to identify potentially hazardous near-Earth asteroids, scanning the sky nightly for movement. By the time Atlas flagged 3I Atlas, the object had already crossed inside Jupiter's orbit and was inbound. Had it been slightly smaller or taken a different angle, it might have passed by entirely unseen. This underscores our observational blind spot. We excel at spotting objects that approach near Earth. We are far less adept at tracking those that skim the outer reaches or zip past quickly. Interstellar bodies do not loiter. They are unbound to the Sun, racing through the system on hyperbolic paths in mere months, instead of decades. Detecting them requires a blend of luck, wide sky coverage, and rapid follow-up observations to lock down their trajectories. The very fact that 3I Atlas was caught at all is a testament to the power of survey astronomy. This discovery validates years of investment in all-sky projects. ATLAS, the Zwicky Transient Facility, Pan-STARRS, and soon the Vera C. Rubin Observatory. Rubin, set to begin operations in the next few years, will transform the field. Its massive camera will photograph the entire visible sky every few nights, sensitive enough to capture objects much fainter than any current survey can see. If interstellar objects are as common as theoretical models indicate, Rubin could discover dozens, perhaps hundreds, over its lifetime. That shift from a handful of rare case studies to a robust statistical sample will finally let us answer deeper questions. What are interstellar bodies typically made of? Are their compositions familiar or exotic? Do they stream in from particular regions of the galaxy? What can their directions reveal about the structure of the interstellar medium and nearby stellar nurseries? Even without solving its own mysteries, 3I Atlas is already instructing us. It's teaching about survey cadence, the necessity of lightning-fast orbital calculations, and the benefits of coordinating across multiple wavelengths and platforms. The Hubble Space Telescope grabbed images in July. Ground-based observatories tracked it through August and September. Mars orbiters attempted observations in early October. This was a multi-layered campaign, spanning space-based instruments and planetary assets, a proof of concept for how the scientific community can mobilize around a sudden interstellar arrival. Yet it also laid bare our shortcomings. During the Mars window, Earth-bound telescopes were hampered by low solar elongation. The comet was too close to the Sun's glare. Mars orbiters had a clear geometry, but were built for planetary science, not for capturing fast-moving comets from another star. Observing 3I Atlas was an opportunistic add-on, not a primary goal. That leads us directly into operations and mission design. If more interstellar objects are expected, and we can safely say they are, it's time to bake rapid response capacity into missions from the outset. Mars orbiters could be equipped with modest wide-field imagers or spectrometers optimized for transient events. Earth-orbiting telescopes might reserve discretionary time for sudden, high-priority interstellar targets. There's precedent. Both Hubble and the James Webb Space Telescope have directors' discretionary time to allow for unplanned observations. But even these mechanisms take days or weeks, and by then the object's geometry may no longer be ideal. What we need are pre-approved templates and automated triggers. When an interstellar object is detected, the system should automatically say, "Here's the orbit. Here are the available instruments. Execute observation plan within 24 hours. No committee delays, no paperwork, just." The Mars window for 3I Atlas highlighted the power of having observers stationed elsewhere. When Earth's view was blocked, Mars still had a line of sight. That's a spatial advantage. Future missions, JUICE, heading for Jupiter's moons, or Psyche bound for the asteroid belt, could provide outer solar system vantage points Earth simply cannot match. The same principle extends to speculative interstellar probes. If one day we send a craft to another star, it could double as an early warning and monitoring outpost for interstellar visitors headed our way. It's a far-off prospect but worth planning for. Transparency and communication form the other major lesson. The shutdown, no matter how one interprets it, exposed a weakness. NASA's public-facing systems went dark, precisely as a scientifically intriguing event unfolded. Its own continuity plan says it clearly during funding lapses. Websites, social channels, and broadcasts go offline. This is not evidence of conspiracy, it's written policy, but the optics are terrible. Silence breeds speculation. People assume something is being hidden when in reality, it's just bureaucracy. Contrast this with the European Space Agency. During the same period, ESA continued posting updates about its Mars Express and ExoMars Trace Gas Orbiter campaigns. NASA's silence and ESA's openness created an asymmetric picture. That asymmetry fed conspiracy theorists primed by Oumuamua to expect secrecy about interstellar objects. The takeaway: transparency during anomalies or shutdowns isn't optional, it's vital for public trust. Even a simple statement, "We're observing, data is being collected, results will be shared," beats total silence. Future shutdowns should include contingency plans for public communication, a skeleton crew maintaining a basic status page, minimal updates on a social channel, anything. The cost of such a system is negligible compared to the reputational damage of appearing secretive. And if a real emergency occurs, the current policy could delay critical public information exactly when it's needed most. These events also highlight the question of data policy. Most planetary mission data is released months or years after collection, a standard practice that gives science teams a proprietary window, but transient interstellar events don't wait. By the time data hits the archive, the object may be gone, or too faint for follow-up. A better approach would be rapid release raw data for high-priority targets. Post images and spectra within days, even if uncalibrated. The broader community can help sift for anomalies far faster than a small mission team. If it's normal, great, everyone moves on. If it's unusual, at least the opportunity for immediate follow-up isn't lost. The Mars window also showed the power of international cooperation. ESA's openness was encouraging, but coordination remains ad hoc. If interstellar objects become commonplace, the world will need a standing international framework for sharing observations, something akin to the International Astronomical Union's designation system for comets and asteroids, but expanded. A network linking space agencies, ground observatories, and amateurs into a single, rapidly activated platform. When an interstellar object is flagged, the system lights up, observation plans are distributed, data streams pooled, results cross-checked. No one nation owns the discovery. It's a global scientific target. That requires more than goodwill. It demands formal agreements, memoranda of understanding, and pre-negotiated data sharing rules. Right now, ESA and NASA cooperate on some projects, but compete on others, and the bilateral data exchange is slow. If we want to be prepared for the next 3I Atlas, or something stranger, we need the infrastructure in place before the object arrives, not after. Then there's the speculative but inevitable resource question. If a future interstellar object is truly metal-rich, a fragment of a planetary core made of iron and nickel,
What happens? The economics of asteroid mining are already under debate for solar system bodies. Interstellar objects add an even sharper twist. They move at extraordinary speeds. Interception windows are short. The required delta V is punishing. It's not feasible today, but the scientific payoff would be immense. A physical sample from another star system brought to Earth orbit would eclipse any meteorite ever found. Legally, the Outer Space Treaty forbids national sovereignty over celestial bodies, but it doesn't prohibit extraction or use of resources. Interstellar objects sit in the murkiest territory of all. They aren't part of any star system and are simply passing through. If you can catch one, can you keep it? Probably, but the ethics remain unsettled. Preparing future missions for interstellar object science doesn't require exotic new technology. You'd outfit them with wide-field cameras to detect and track, spectrometers to analyze composition, photometers to measure brightness variations, perhaps radar if close enough. These are off-the-shelf instruments. The real challenge is agility, reallocating resources quickly enough to capitalize on a fleeting opportunity. Mars orbiters could do it tomorrow if mission rules allowed. Earth-orbiting telescopes already do it under discretionary time. What's missing is a cultural shift. The realization that interstellar objects are common enough to justify designing missions with them in mind from the start. Public understanding matters just as much. One reason theories about metallic cores or alien artifacts take hold is that most people lack an intuitive sense of how uncertain comet measurements can be. When the size estimate reads 0.35.6 kilometers, the public doesn't see a scientific uncertainty range. They see a menu of possible truths and pick the one that excites them. Communicators need to do a better job of explaining error bars and making "we don't know yet" a normal, respected answer. Otherwise, every gap in data gets filled with the most dramatic interpretation. Cue the alien mothership headlines. And that brings us to where we are now. 3i Atlas has proven that interstellar object science is real, happening now, and that we're still not fully prepared. We have the tools, we have the interest. What we lack is speed, coordination, and transparency. The shutdown acted as a stress test, and we didn't exactly ace it, but we can learn. We can build stronger systems before the next visitor arrives, because it will. The galaxy is filled with these wanderers, and our surveys improve every year. And if one of them turns out to be more than a comet, something genuinely new, will need all that infrastructure, openness, and collaboration to decipher it. The question isn't if we'll encounter something extraordinary, it's whether we'll be ready when we do. Which brings us to the next stage. Part 15, Synthesis, Open Ends and Actionable Promises. Let's bring everything full circle. Midnight, October 1st, 20. The US government shuts down. Hours later, the Mars observation window for the interstellar visitor 3i Atlas. Coincidence or cover-up? You came here for an answer. I'll give you one, but it won't be simple, and it won't satisfy everyone, because the truth buried beneath all the data and speculation is that both things can be true at once. The shutdown was real, the silence was procedural, yet the timing created the perfect conditions under which something unusual could be muted or delayed, if there had been anything unusual to delay, and that ambiguity in itself is the story.
That marked the point where the comet reached its closest distance to the Sun, about 1.36 astronomical units, just inside Earth's orbit but not dramatically closer. After swinging past perihelion, the comet arced outward again, slipping behind the Sun from Earth's perspective, and entering what astronomers call solar conjunction. During conjunction, it's essentially invisible from our planet. The Sun's overpowering glare wipes it from view. This blackout persists through most of November. By late November or into December, the comet will emerge on the far side of the Sun, finally far enough from the solar disk for ground-based telescopes to pick it up again. That's the reappearance window, the next opportunity to collect fresh data. As of this moment, early October, we're in a strange limbo. Either the Mars-based observations have already occurred, or they're still being processed. What counts as success depends on which agency you're asking, and how you define a valid observation. None of the detailed data from those attempts has been released yet. That's normal. Raw products from Mars orbiters often take weeks or even months before public release. The government shutdown slowed this even further. Although the spacecraft kept operating, the analysts and archivists who handle the data were temporarily furloughed. They've presumably returned to work now, but a backlog remains. Right now, the comet is at perihelion, the conjunction blackout is beginning, and the big second round of observations is still in the future. All of this means that every hypothesis, every theory and rumor is suspended in unresolved tension, exactly the narrative state a mystery thrives in. But it also gives us a roadmap for what to watch next, a set of checkpoints. If you truly want to sort coincidence from cover-up, here's how. First, monitor the Minor Planet Center. The MPC is the official clearinghouse for observations of asteroids and comets. Every positional measurement from a telescope anywhere on Earth gets submitted there and is published in the Minor Planet Electronic Circulars or MPECs. These are public records you can read yourself. Since its discovery in July, 3I Atlas has had a steady stream of MPEC updates. Each one combines measurements from multiple observatories, gradually refining its orbit. If something anomalous happened during the Mars window, significant perturbations or unexplained accelerations, they'll show up in the orbital solutions published in November and December. The MPC doesn't spin the story, they just print the numbers. If independent datasets all converge, that's a sign the orbit fits the model. If residuals appear or if the numbers diverge in unexplained ways, that's a red flag. Second, keep an eye on the European Space Agency's Mars mission pages. ESA is generally diligent about releasing instrument updates and raw images. If Mars Express or the Trace Gas Orbiter recorded anything noteworthy, it will surface eventually, maybe not instantly, maybe not fully analyzed, but at least as unprocessed data. When it does, compare it to the planned observation windows, match timestamps, predicted brightness, and motion. If everything aligns, that supports the straightforward explanation. If it doesn't, that's when harder questions begin. Third, track NASA's post-shutdown upload. Once appropriations resume, NASA gradually posts the data it couldn't release during the funding lapse. Look at the 3I Atlas mission page on nasa.gov. Scan Hubble and JWST observation logs. Search for any mention of the Mars Reconnaissance Orbiter or MAVEN attempting comet observation. Even without full analysis, metadata, instrument, timestamps, coordinates should exist. If those logs are missing or show odd gaps that don't match standard shutdown procedures, that's not proof, but it's definitely unusual. Fourth, watch the scientific literature. The Hubble team that imaged 3I Atlas back in July released an early preprint on arXiv.org. That's where new results show up first. Search for 3I Atlas or C2025N1. If new papers appear with data from the Mars window, read them carefully. Check authorships, acknowledgements, and instrument notes. Peer reviewers examine the data. If something's off, it will either get flagged or publicly debated. Science is messy, slow, but ultimately transparent. Fifth, be ready for the comet's reappearance. When 3I Atlas emerges from conjunction in late November or early December, both professionals and amateurs will target it again. Images will get posted, brightness measured, spectra taken when possible. Follow forums like Cloudy Nights or comet-focused Twitter account. If the comet's light curve behaves as predicted and its coma evolves normally, that strengthens the mundane explanation. If brightness spikes, spectral lines surprise, or the coma behaves oddly, people will notice and amplify it. Sixth, you can even try your own experiment. Earlier I mentioned that amateur radio astronomers could search for artificial signals. It's a long shot, but feasible. If you have a software-defined radio and a decent antenna, you can capture a dynamic spectrum pointed at 3I Atlas during its reappearance. Use GPS timestamping so your data can be compared globally. Open source tools like GNU Radio or SDRRAN make it possible. Share raw files. If 5 observers in 5 countries record the same drifting signal at the comet's Doppler shifted frequency, that would be extraordinary. Nobel level extraordinary. It hasn't happened yet, and almost certainly won't, but the ability to try matters. It proves the search is open, not hidden behind classified walls. Now let's rank the major hypotheses. Hypothesis 1. Simple bureaucratic timing. The shutdown paused NASA's public communications, but not its data collection. Results will emerge on a normal schedule. This fits the known facts with minimal assumptions. Boring but likely. Falsification would come if ESA or another agency released data contradicting predicted behavior or if orbital fits show anomalies NASA failed to disclose. Hypothesis 6. Environmental effects. Solar wind gusts, or a subtle Martian gravitational influence, could temporarily alter the comet's brightness or orbit. Comets are volatile. They respond to their surroundings. Even a tiny nudge at 30 million kilometers could appear in high-precision astrometry. Falsification would be the absence of brightness spikes, spectral changes, or orbital residuals in Mars data. Hypothesis 2. An unusually dense or metallic core. Speculative but grounded in early unconfirmed reports of nickel emissions and high mass estimates from Hubble data. Differentiated bodies do exist, and fragments of their cores could travel interstellar space. But if better size and albedo measurements shrink the mass estimate, and spectra reveal only standard cometary volatiles, this collapse. Hypothesis 5. Black budget data capture. The notion that Mars window data exists, but is classified. This is inherently hard to evaluate because secrecy leaves no fingerprints. There's no leak, no whistleblower, no document. Falsification. Normal, time-stamped data releases, post-shutdown consistent with unclassified operations. If data never appears, it could mean it was never taken or that it failed, not necessarily that it's hid. Hypothesis 4. Third-party intervention. A covert spacecraft flyby or sample retrieval during the Mars window. This would require extraordinary technology, global secrecy, and murky motivation. Falsification would be consistent, multi-agency orbital fits with no anomalies or Doppler outliers, ruling out significant interference. Hypothesis 3. Engineered artifact. 3I Atlas isn't a comet at all, but a relic probe from another civilization. This is the boldest claim with the heaviest burden of proof. Right now, no verified signals, no unexplained structural features, no hard evidence. The idea persists, because Oumuamua opened the door and because RV Loeb continues pressing for aggressive observation campaign. Falsification. If its light curve, spectrum, and trajectory all match natural comet behavior and competent searches detect nothing, the artifact hypothesis loses footing. That's the hierarchy. Mundane first, exotic last. That's how to approach any true mystery. Start simple, escalate only if simplicity fails. So what's next? Here's the promise. When new data drops, images, papers, logs, we'll revisit it. Did NASA post Mars Reconnaissance Orbiter, or high-rise thumbnails from the window? Do timestamps align? Do images show anomalies, or just a fuzzy dot? Did ESA release HRSE or CASIS data? Does it match predictions? Did the MPC's orbital solution converge with post-perihelion data? Did residuals shrink or grow? Are non-gravitational parameters consistent without gas? We'll check each box, compare each claim to each receipt. If everything checks out, the mystery was mainly timing and communication gaps. If discrepancies persist, if data contradicts models or remains missing, then the mystery deepens. No PhD required. No classified briefings needed. Just patience, a browser and the willingness to match a timestamp to a calendar. The verification tools are public. Use them. And remember this final point. If 3I Atlas were truly engineered, if it were a probe, a relay, a piece of ancient alien infrastructure, it wouldn't be hidden in one dataset. It would leave a trail across wavelengths, across telescopes, across months of observation. It would show itself in astrometry, photometry, spectroscopy, in ways ice and dust cannot mimic. That's the trail we're following. Not rumors but data. And the trail is public, or will be, once conjunction ends, and observations resume. So when NASA's websites light up again, when the press releases flow and the backlogged images post, we'll find out, was the silence just policy, or something more? Was 3I Atlas a comet caught in bad timing, or the first act of something strange? Until then, keep watching the sky, keep checking the sources, and keep asking the uncomfortable questions. The universe owes us nothing. No easy answers, but if we're persistent, careful and honest about what we know and what we don't, we might find the truth anyway. The shutdown is over, the comet is rounding the sun, the data is coming, and we'll be here, ready to piece it together. This is normally where I'd sign off with see you next time, but next time is already on the calendar, late November or early December, when 3I Atlas emerges from behind the sun, and telescopes lock on again.
That's when the answers begin. If the answers are mundane, just a comet, that's okay. Because the investigation itself, the collective effort to understand, is never boring. That's science. That's how we separate signal from noise and keep ourselves honest. But if the answers aren't mundane, if even one measurement defies the models, one signal can't be explained away, then this story is only beginning, and you'll want to be here for what comes next. So mark your calendars, follow the sources, download the data when it drops, compare notes with others, piece the puzzle together, and when the picture emerges, we'll know whether October 1st, 2025, was just another night of bureaucratic darkness, or something designed. We'll know whether 3i Atlas was a comet, or a calling card. Until then, the mystery lives in the gap between what was seen and what was hidden, between what was spoken and what remained silent, between coincidence and cover, and that gap, that uncertainty, is where the best stories live. The lights are flickering back on, let's see what they reveal.